Welcome back to the Sleepy Thought Channel. If you are new here, this is a place built for quiet minds and tired eyes, a channel where curiosity and rest find each other at the end of a long day, where the strange and beautiful facts of this universe we share become something soft enough to carry you into sleep. People have been finding their way here from all over the world, from different time zones and different seasons, different languages and different lives. And what brings them together is the same simple thing that brings you here tonight, the wish to let go of the day, to breathe more slowly, to be curious without urgency, and to let the natural wonder of existence be a comfort rather than a question that demands an answer right now. Tonight, we are not going to talk about the things science has figured out. We are going to do something a little different, something that might feel unusual at first, but that I think you will find genuinely comforting. Tonight, we are going to sit with the mysteries, the things that the greatest minds on Earth have studied for decades, sometimes centuries, and still cannot fully explain. Not because science has failed, but because the universe is so much larger, so much stranger, so much more layered than any one generation of thinkers could ever hope to unravel all at once. There are 100 of these mysteries waiting for you tonight. 100 open doors into the unknown, and you do not have to walk through any of them all the way. You only have to listen. There is something deeply peaceful about not knowing something that feels, if you let it, like standing at the edge of a very wide ocean on a very calm evening, watching the water stretch away from you into the horizon, the waves arriving gently one after another, carrying no urgency at all. The mystery is not there to frighten you. It is there to remind you that the world is still alive with wonder, that there are still stories waiting to be told, still questions hanging soft and luminous in the air, like lanterns over a still lake. Science is not a destination. It is a walk, a long and quiet walk through territory. It keeps revealing new rooms just beyond the ones you thought were the last. And the fact that those rooms are still there, still unopened, is not a failure. It is an invitation. So settle in now. If you have a blanket, pull it a little closer. If the light is low, let it stay that way. You do not need to hold on to any of this. You do not need to memorize a single word. Just let these mysteries wash over you one by one, the way water finds its way through stone. Slowly, gently, without effort. Let your breathing find its own rhythm. Let your thoughts soften at the edges. Your shoulders fall. Let the day you carried begin to set down its weight. And when sleep comes for you, let it come. If these quiet journeys mean something to you, the kindest thing you can do is leave a small note in the comments or share this with someone who needs a little rest tonight. One sleepy soul finding another is how this community grows, and it means more than you know. But for now, there is nothing you need to do. Only rest, only wonder, only the soft and endless mystery of a universe that still has so much left to tell us. Let us begin. Nobody knows why we sleep. This might seem like a strange place to start, given that sleep is exactly what you are trying to do right now. But consider this for a moment. Sleep takes up roughly 1/3 of every human life. A person who lives to be 90 years old will have spent about 30 of those years unconscious. And yet, despite decades of research, despite entire scientific fields devoted to the study of sleep, we still do not have a complete and agreed upon answer to the simplest possible question: why do we do it? We know sleep matters enormously. We know the brain clears waste products while we rest, flushing out cellular debris through a kind of drainage system called the lymphatic system that appears to be especially active during deep sleep. We know memories are consolidated during certain sleep stages, that the events and learning of the day are replayed and integrated while we are unconscious. We know the immune system does critical repair work in the hours we are unconscious, and that chronically sleep-deprived animals die at rates that suggest sleep is not optional in any meaningful biological sense. But whether any of these functions alone, or all of them together fully, explain why sleep evolved in the first place, why animals across almost every branch of life spend hours each day, completely vulnerable and unaware is still genuinely uncertain. Even the simplest single-celled organisms appear to have rest states. Sleep is one of the most universal things in the animal kingdom. More universal than eyes, more ancient than bones. And it is still at its heart a mystery. You are doing something right now that no one can fully explain. And yet, it is the most natural thing in the world. We do not know why. We dream even deeper than sleep itself is what happens inside it. Every night most people enter a state where the mind becomes a storyteller, conjuring people and places, conversations and colors, fears and longings. Entire worlds that feel completely real until the moment they dissolve. Conversation with someone who passed away years ago, rendered in perfect detail. A landscape that has never existed anywhere on Earth. A version of your childhood bedroom with a door that leads somewhere impossible. We call these dreams, and we have been fascinated by them since the earliest days of recorded history. Ancient Egyptians believed dreams were messages from the gods. The Greeks built entire temples where people would sleep in hopes of receiving divine guidance through their dreams. Iroquois organized aspects of their society around the symbolic content of dreams. And today, thousands of years later, neuroscientists still cannot tell you with certainty what dreams actually are or why we have them. There are theories. One suggests that dreaming helps process emotions, giving the sleeping mind a safe space to rehearse and integrate difficult experiences. Another proposes that it is the brain rehearsing for possible future events, running simulations of challenges that might be encountered. Some researchers believe dreams are simply a byproduct of the brain's activity during sleep patterns, firing without any deeper purpose, the mind generating narrative from noise, the way we see faces in clouds. But none of these explanations has been proven, and none fully accounts for the richness and strangeness of dream experience. For the way dreams can feel more emotionally real than waking life, even while being physically impossible. The dreaming mind remains even now one of the most beautifully unexplored territories in all of science. Consciousness itself has no scientific explanation. You are aware right now, you know that you are here, that you are listening, that there is something it feels like to be you in this moment. That simple fact, the sheer existence of subjective experience, is called consciousness, and it is arguably the deepest unsolved problem in all of human knowledge. Philosophers call it the hard problem, because no matter how much we learn about neurons and brain activity, no matter how precisely we map the circuits of the mind, we still cannot explain how physical processes in the brain give rise to the felt quality of experience. Why does seeing the color blue feel like something? Why does hearing music move us? Why is there an insight to experience at all? Some scientists believe consciousness will eventually be explained by neuroscience. Others believe it requires an entirely new kind of science we have not yet invented, and a few believe it may never be fully understood. Not because the universe is hiding something, but because consciousness may be the one thing that can never fully step outside itself and see itself clearly. Whatever the truth turns out to be, there is something quietly beautiful about it. You are a mystery to yourself, and you always have been. We cannot explain why there is something rather than nothing before the universe existed. What was there before matter, before energy, before space and time themselves? What came before? This is the oldest and perhaps most unanswerable question in all of philosophy and physics. The current best scientific understanding suggests that the universe began approximately 13.8 billion years ago. In an event we call the Big Bang, a moment when everything that exists expanded from an unimaginably dense and hot state. But science cannot yet tell us what existed before that moment, or whether the word before even makes sense in a context where time itself had not yet begun. And more fundamentally, why does anything exist at all? Why is there a universe with its stars and its silence and its sleeping creatures, rather than simply nothing? There are ideas. Some physicists suggest that quantum fluctuations in a primordial nothingness could spontaneously give rise to something. Others propose that the universe is eternal, in some form cycling through endless expansions and contractions. None of these fully closes the gap. The question of why there is something rather than nothing remains as it always has. One of the most profound mysteries a human mind can hold. Nobody knows what dark matter actually is. You might have heard that most of the universe is invisible. That is not a metaphor or an exaggeration. Scientists have determined through the careful observation of how galaxies move and how light bends around massive objects that the ordinary matter we can see, the stars, the planets, the gas clouds, everything made of the same stuff as you. And this room accounts for only about 5 of the total matter and energy in the universe. The other roughly 27% is something called dark matter. It exerts gravity. It affects the large-scale structure of the cosmos, and it has never once been directly detected or observed. We know dark matter exists because of what it does, but we have no idea what it is made of. It could be exotic particles that interact with ordinary matter only through gravity. It could be something even stranger, something that does not fit into any of our current models of physics. For decades, experiments have searched for dark matter in underground laboratories, in data from particle accelerators, in signals from space. So far, nothing. The majority of the matter in the universe remains completely unknown to us, as quietly present as something sleeping just out of sight. Dark energy is even more mysterious. If dark matter is puzzling, dark energy is even more so. The remaining roughly 68 of the universe is composed of something called dark energy, a mysterious force that appears to be causing the expansion of the universe to accelerate. When scientists first discovered this acceleration in the late 1990s, it genuinely shocked the physics community. The universe was not just expanding, it was expanding faster and faster, pushed apart by something no one had predicted and no one could yet explain. The simplest description we have for dark energy is that it is a property of space itself, a kind of energy built into the fabric of the universe that pushes everything apart. But this explanation raises more questions than it answers. Where does this energy come from? Why does it have the particular value it has? Why does it seem to be constant across all of space and time? Nobody knows. Dark energy is the largest ingredient in the universe, and it remains almost entirely unknown. We do not know where life first came from. Life is everywhere on Earth, in the soil beneath your feet, in the deepest ocean trenches, in clouds of steam above volcanic vents, in pools of acid in frozen glaciers. Life finds a way, and yet despite knowing an enormous amount about how life works, how cells divide, how DNA codes for proteins, how evolution shapes living things over time, we still do not know how life first started. How did the first self-replicating molecule come to be? How did chemistry, which is just atoms and their interactions, cross the boundary into biology, which involves something that feels entirely different? How did the first living thing emerge from a world that was entirely not alive? There are plausible ideas. The RNA world hypothesis suggests that early RNA molecules may have acted as both information carriers and catalysts, jump-starting the process. Hydrothermal vents on the ocean floor have been proposed as cradles of early life, where heat and chemistry collide. Some scientists have even suggested that life may have arrived on Earth from elsewhere in the cosmos, carried on meteorites. But the actual origin, the specific sequence of events that turned chemistry into life, remains one of the greatest unsolved mysteries in all of science. The placebo effect works in ways we cannot fully explain. This is one of the gentler mysteries in science, and one of the most quietly remarkable. A placebo is an inactive treatment, a sugar pill, a saline injection, a procedure that does nothing medically. And yet, across hundreds of thousands of clinical studies, patients who receive placebos often improve not just a little, sometimes dramatically. People report less pain, fewer symptoms, genuine measurable changes in their bodies, all from something that should, by all conventional logic, do absolutely nothing. The mind and body are clearly talking to each other in ways we do not fully understand. Expectations seem to shape biology, belief influences chemistry. The relationship between what a person thinks is happening to them and what their body actually does is far more intertwined than science once assumed. And the deeper question of how exactly a thought or a belief translates into a physical change in the body has never been fully answered. The placebo effect is real, it's powerful, and it is still in many ways a mystery. Quantum entanglement has no satisfying explanation. Here's something extraordinary. Two particles can become entangled, meaning their properties are linked in such a way that measuring one instantly determines the state of the other, no matter how far apart they are. Not after a delay, not at the speed of light instantly. Albert Einstein called it spooky action at a distance, and he was deeply uncomfortable with it because it seemed to violate the principle that nothing can travel faster than light. And yet experiment after experiment has confirmed that entanglement is real. It happens. It is not a measurement artifact or a misunderstanding. Two particles genuinely do seem to be connected across any distance in a way that has no good physical explanation. Quantum mechanics describes how entanglement works mathematically, and those descriptions are extraordinarily accurate, but they do not explain why entanglement behaves this way or what is actually happening in the space between two entangled particles. What is the connection? Is there a connection in any physical sense? Or is reality itself different from how we imagine it? Physicists have been debating this for nearly a century, and the answer remains genuinely open. We do not know what happens inside a black hole. Black holes are among the most dramatic objects in the universe, regions where gravity becomes so intense that not even light can escape. We know they exist. We have observed their effects on surrounding matter. We even have photographs, or rather images reconstructed from radio telescope, data of the shadow cast by the black hole at the center of our own galaxy. But what actually happens inside a black hole beyond the event horizon, the point of no return, remains completely unknown. Our best theories of physics, general relativity, and quantum mechanics break down inside black holes. They produce what physicists call infinities, results that make no physical sense, which is usually a sign that the theory is incomplete. What lies at the heart of a black hole? Is there a singularity, a point of infinite density? Or does quantum physics intervene somehow, preventing that infinity? Does information survive in some form? Or is it truly destroyed? These questions matter not just for black holes, but for our entire understanding of reality. And none of them have been answered. The brain creates a sense of self from nothing. You have a sense of being you, not just a body, not just a collection of thoughts, but a self, a continuous identity that wakes up each morning and recognizes itself, that has memories of a past and expectations of a future, that feels like the same person it was yesterday and the same person it will be tomorrow. This sense of self feels absolutely fundamental, the most basic thing about human experience. And yet neurologically, it is not clear where it comes from or what it actually is. The brain is a network of approximately 86 billion neurons. There is no single place where the self lives, no central processor generating your sense of identity. It seems to emerge from activity distributed across the whole system, a kind of story the brain tells itself about itself, but how that story creates the felt experience of being someone. How distributed neural activity becomes a continuous first-person perspective is a question neuroscience has not yet answered. You are a mystery to the very organ you would use. To solve the mystery, we cannot explain why music moves us emotionally. There is a moment that many people know when a piece of music reaches something deep. A swell of strings, a voice cracking just so, a melody, arriving at exactly the right moment, and something in you responds. Your chest tightens, your eyes sting, goosebumps rise along your arms. Experience is real and universal across cultures and throughout human history. But why music has this power over us is something science still struggles to explain. Music is vibrations in air. It is patterns of sound. There is no obvious evolutionary reason why certain arrangements of sound, waves should reach into our emotional core the way they do. Various theories have been proposed that music mimics the emotional qualities of the human voice, that it triggers the brain's reward pathways in ways that feels similar to other pleasures, that it creates patterns of expectation and release that the brain finds deeply satisfying. But none of these fully accounts for why a particular chord progression at a particular moment can make a grown person weep. Music reaches somewhere that science has not yet fully mapped. Or lightning is real, and nobody knows what it is. Thousands of people across many countries and centuries have reported the same strange phenomenon during or after thunderstorms. A glowing ball of light, sometimes the size of a grapefruit, sometimes as large as a beach ball, appears and drifts silently through the air. It may pass through windows without breaking them. It may float inside buildings. It may hover for several seconds or even minutes before vanishing, sometimes silently, sometimes with a pop. This is called ball lightning, and it has been reported for centuries. There are credible accounts from pilot scientists and careful observers. And yet, despite all of this, science has not reached a consensus on what it is. Laboratory experiments have produced similar-looking phenomena. Various theories exist involving plasma microwave radiation, oxidizing aerosols, and more, but none of these explanations has been definitively confirmed. And none fully accounts for all the features that witnesses describe. Ball lightning remains classified as a genuine atmospheric mystery, one that has outlasted many confident predictions of an imminent explanation. Gravity is the weakest force, and we do not know why. There are 4 fundamental forces in nature: gravity, electromagnetism, and the strong and weak nuclear forces. Gravity is the most familiar, the force that holds you to the Earth, that keeps the planets in orbit, that shaped every galaxy in the universe, and it is also by a staggering margin the weakest of the 4. Electromagnetism is around 10 to the power of 36 times stronger than gravity. That is a number so large, it is essentially impossible to feel intuitively. Why would the force responsible for organizing the large-scale structure of the entire cosmos be so much weaker than the other forces that govern the atomic world? Why does it exist at the scale it does? Some physicists have speculated that gravity may be leaking into other dimensions, spreading itself thin across realities we cannot perceive, which would explain why we experience it as so weak. Others hope that a future theory of quantum gravity might reveal a deeper reason for gravity's apparent feebleness. For now, the hierarchy problem, as physicists call it, remains unsolved. We do not know why birds can navigate using the Earth's magnetic field. Every year, billions of birds migrate across thousands of miles, navigating with an accuracy that would be impressive with GPS and extraordinary without it. Many species can sense the Earth's magnetic field and use it as a compass, and the mechanism behind this ability is one of the more delightful unsolved mysteries in biology. Current evidence points to a quantum mechanical process involving cryptochrome, proteins in the bird's eyes, where quantum entanglement between electrons may allow the birds to essentially see the magnetic field as a pattern overlaid on their vision. This is both wonderful and deeply strange. It suggests that some living creatures may be using quantum physics for navigation, a connection between the weird world of quantum mechanics and the biology of a songbird flying south for the winter. The precise details of how this works and how evolution arrived at such a solution remain an open question. The Fermi paradox has no satisfying answer. The universe is roughly 13.8 billion years old. It contains somewhere between 100 billion and 200 billion galaxies. Each galaxy contains hundreds of billions of stars. Many of those stars have planets. The conditions for life as we know it exists in abundance. Given all of this, it seems almost mathematically impossible that Earth would be the only place where intelligent life has developed. Even if only a tiny fraction of planets developed life, and an even smaller fraction of those developed intelligence, and an even smaller fraction of those developed technology capable of communication across space, the sheer numbers of stars in the observable universe suggest there should be many civilizations out there. And yet, despite all of our searching, despite decades of listening with radio telescopes for signals from other intelligence, we have found no unambiguous signal, no confirmed contact, no clear evidence that anyone else is out there. The sky is silent. This is the Fermi paradox, named for the physicist Enrico Fermi, who supposedly asked at a lunch table, "Where is everybody?" Many possible answers exist. Perhaps intelligent life is far rarer than we assume. Perhaps the emergence of complex multicellular life is extraordinarily improbable and has happened only once in the observable universe. Civilizations inevitably destroy themselves before becoming detectable through war, climate catastrophe, or technological accident. Perhaps they have chosen silence, hiding from the galaxy for reasons we cannot yet understand. Perhaps they are here, and we are not recognizing them. Perhaps the distances are simply too great for any communication to have reached us. Yet none of these answers is satisfying on its own, and none has been confirmed. The silence of the cosmos remains one of the most haunting, unsolved problems in all of science. We do not fully understand how anesthesia works. Every year, millions of people undergo surgery under general anesthesia. They are given a drug or combination of drugs that render them unconscious, free from pain, and entirely unaware for the duration of the procedure. Anesthesia is one of the most transformative discoveries in the history of medicine. And the remarkable thing is that even now, anesthesiologists do not fully understand exactly how it works. We know which drugs to use and how to use them safely. We know what they do to brain activity at a broad level, but the precise mechanism by which these substances switch off, consciousness, and the exact nature of what consciousness actually is during general anesthesia remains an open question. The fact that we can reliably produce some consciousness without fully understanding how we do it is a curious reflection of medicine's relationship with the deepest mysteries of the mind. Nobody knows why some people are left-handed. Somewhere between 10 and 15 of the human population is left-handed. This proportion has been remarkably consistent across cultures and throughout recorded history. There is clearly something biological underlying handedness as it runs in families and is influenced by genetics. But despite years of study, the specific genes involved, and the complete developmental pathway that leads a person to favor one hand over the other have not been fully pinned down. More puzzling is why the minority exists at all. Most asymmetric traits in biology go strongly one way. The fact that left-handedness has persisted at a fairly constant minority percentage across all of human history suggests it may have offered some advantage, perhaps in combat or social dynamics that balanced out against the advantages of the majority. But this remains speculation. Why you are the handed person you are is still not fully understood. The universe appears finely tuned for life, and we do not know why. The fundamental constants of the universe, things like the strength of gravity, the mass of electrons, the value of the electromagnetic force appear to be precisely calibrated in ways that allow stars, planets, and ultimately life to exist. If any of these constants were even slightly different, the universe would be utterly inhospitable. Stars would not form, atoms would not be stable, carbon would not exist. The universe as we know it would either collapse immediately or expand so fast that matter could never clump together at all. This extraordinary precision is called fine-tuning, and it raises an obvious question: why? One answer is the multiverse, the idea that our universe is just one of an enormous or infinite number of universes with different physical constants, and we naturally find ourselves in one that happens to allow our existence. Another answer is that some principle we do not yet understand constrains the constants to be what they are. Some see in fine-tuning an argument for a designer of some kind. Science cannot yet distinguish between these possibilities. The fine-tuning of the cosmos remains one of its deepest and most discussed mysteries. We do not know how memory is stored in the brain. You remember things: the face of someone you love, the smell of your childhood home, a moment of unexpected happiness from years ago. Memory is the thread that makes us self-continuous across time, and it is one of the most studied topics in neuroscience. We know that memories involve changes in the connections between neurons, a process called synaptic plasticity. We know certain brain regions, like the hippocampus, are crucial for forming new memories. but the precise physical mechanism by which a memory is encoded, stored, and retrieved, the actual pattern of change in the brain that corresponds to a specific memory, has not yet been fully mapped. There are theories and models, some quite sophisticated, but the engram, the physical trace of a specific memory in the brain, remains elusive. Our rich and vivid experience becomes a physical change in billions of neurons, and how those changes later give rise to the experience of remembering is a question neuroscience is still working to answer. The placebo effect even works when people know it is a placebo. We touched on the placebo effect earlier, but this deserves its own mention because it is one of the stranger discoveries to emerge from recent medical research. In classic placebo studies, patients do not know whether they are receiving a real treatment or an inactive one. The placebo effect was thought to depend on this deception, on the patient's belief that they were receiving something real. But recent research has appended this assumption. In studies where patients are explicitly told they are receiving a placebo pill, told it contains no active ingredient, a significant portion of them still improve. The open-label placebo effect, as it is called, suggests that something about the ritual of treatment, perhaps simply the act of taking care of oneself or the therapeutic encounter with a caring practitioner, is enough to trigger genuine biological responses. The mechanisms behind this are still not understood, and the implications for medicine are still being worked out. We cannot explain why some people need far less sleep than others. Most adults need somewhere between 7 and 9 hours of sleep to function well. But a small number of people, perhaps 1 or 2 of the population, seem to function perfectly fine on 6 hours or less, and they do so without any apparent negative health consequences. These natural short sleepers, as they are called, are not simply tolerating sleep deprivation the way most people would. Their bodies genuinely seem to require less sleep. Researchers have identified genetic variants that appear to be associated with this trait, but the full picture of how these genes alter sleep architecture and why evolution would have preserved this variation in the population is not yet clear. Sleep itself is mysterious enough. Why some people seem to need so much less of it is a smaller mystery nested within the larger one. We still do not know what causes migraines. Migraines affect roughly 1 billion people worldwide, making them among the most common and debilitating neurological conditions in existence. And yet, despite their prevalence and the enormous amount of research devoted to understanding them, exactly what causes a migraine is still not fully understood. We know they involve changes in brain activity, including waves of electrical suppression called cortical, spreading depression and changes in blood flow and inflammation. We know they involve the trigeminal nerve system and a molecule called calcitonin gene-related peptide. Drugs targeting this molecule have been helpful. But why migraines start, what the fundamental biological mechanism is, and why some people are so much more prone to them than others remains an active area. Research without a complete answer. Ocean rogue waves were once considered a myth for centuries. Sailors told stories of monstrous waves, walls of water, rising suddenly from a calm sea 2 or 3 times the height of surrounding waves, appearing without warning and capable of destroying ships in an instant. For a long time, scientists considered these stories folklore or exaggeration. The mathematical models of ocean waves did not predict such events as anything more than vanishingly rare. And then, on the first day of January, in 1995, a wave was recorded by instruments on the Drobna oil platform in the North Sea. It measured over 25 meters high in conditions where surrounding waves were perhaps 12 meters. This was the first scientifically documented rogue wave, and it proved the sailors right. Rogue waves are real. They occur far more often than the classical models predicted. Why exactly they form? The precise combination of conditions that can cause a single wave to suddenly and unpredictably rise to enormous heights is still a subject of active and ongoing research. The origins of language are unknown. Language is one of the things that most clearly separates humans from other animals. It allows us to share experience, coordinate behavior, transmit knowledge across generations, tell stories about things that are not present, or that never existed, or that might exist in the future. Language is at the root of everything we call civilization. And yet, how it originated, how the first human minds developed the capacity for symbolic communication and grammatical structure, is one of the hardest problems in the study of human evolution. Language leaves no fossils. We can look at ancient artifacts and infer things about the minds that made them. We can study the genetics of language-associated brain regions. But the actual emergence of language in the human lineage, the moment or gradual process by which grunts and caws became words and sentences, remains hidden from us somewhere in a past we cannot fully recover. We do not understand why the arrow of time points in one direction. Time moves forward. This is so fundamental to experience that it barely seems worth stating. Memories are of the past, not the future. Things age and decay. They do not spontaneously become younger. Eggs break, but they do not unbreak themselves. The direction of time from past to future feels like an absolute feature of reality. And yet almost all of the fundamental laws of physics are time symmetric. They work the same whether time runs forward or backward. There is nothing in the equations of quantum mechanics or electromagnetism or general relativity that picks out the preferred direction of time. The one exception is a law of thermodynamics that says entropy disorder tends to increase over time. But why entropy was so low in the early universe, which is what allows it to increase, and what this has to do with our felt experience of time flowing in one direction, is something physics has not fully resolved. We cannot explain what happens during near-death experiences. People who come close to death and are then revived through cardiac resuscitation, near drowning, or other medical emergencies sometimes report vivid and remarkably consistent experiences. They describe floating above their own body and watching medical staff work, sometimes describing details of the scene that they could not have observed from where their body was lying. They describe moving through a dark tunnel toward a brilliant light. They describe encounters with deceased loved ones, warm and immediate, as if no time has passed. They describe a sense of overwhelming peace, more profound than anything they had known in waking life, and a feeling of being told it is not yet their time. They describe a panoramic review of their lives, every significant moment laid out in an instant. These reports come from people across widely different cultures and religious backgrounds, and they show consistent patterns, whether the person was a devout believer or a committed atheist, whether they were young or old, whether their near-death event was expected or sudden. Some explanations focus on changes in brain chemistry and oxygen levels during the dying process, suggesting that the experiences are a kind of neurological event produced by a brain in extreme distress. Others point to activity in specific brain regions, including the temporal lobes, which when stimulated can produce experiences of presence and memory review. Some researchers take seriously the possibility that these experiences represent something that our current neuroscience cannot fully account for. None of these explanations has been definitively confirmed. Near-death experiences remain one of the most personal, most moving, and most scientifically puzzling phenomena that humans report. The strength of the nuclear forces is unexplained by any deeper theory. The strong nuclear force holds together the nuclei of atoms. Without it, every atom in the universe would fly apart in an instant. It is extraordinarily powerful at very short ranges, and the precise strength of this force, why it has the value it does, is something our current physics cannot derive from anything more fundamental. The same is true of the other fundamental forces and their coupling constants. We can measure these values with great precision, and we can observe what would happen if they were different, but we cannot explain why they are what they are. They appear in our equations as numbers we have measured rather than values we have derived. A deeper theory, sometimes called a theory of everything, might eventually explain why the constants of nature are what they are. So far, we do not have that theory. Certain animals can regrow limbs, and we cannot explain all the details of how salamanders can regrow lost limbs. Planaria tiny flatworms can regrow entire bodies from small fragments. Starfish can regenerate arms, some lizards regrow their tails. The ability of certain animals to regenerate complex structures is one of the more extraordinary phenomena in biology. Researchers have made significant progress in understanding the cellular and molecular mechanisms involved. It appears that specialized stem cells and signaling molecules orchestrate the regrowth somehow, knowing what structure to rebuild and where. But the precise way in which cells know what to become, how the regrowth process is coordinated to produce something as complex as a limb, with bones and muscles and nerves all properly connected, is still an active research area with many open questions. Understanding it fully could have transformative implications for human medicine. We do not know what causes certain people to have eidetic memory. Some people can look at a page of text or a complex image and recall it afterward in extraordinary detail, as if the image is still in front of them. This is sometimes called a photographic memory, though scientists prefer the term eidetic imagery. It occurs more commonly in children than adults and is not fully understood. The neural mechanisms that might allow such precise retention of visual information have not been clearly identified. Attempts to confirm the existence of true adult eidetic memory under rigorous scientific conditions have produced mixed results. The few well-documented cases of extraordinary memory that exist in adults tend to involve different mechanisms than the classic photographic model. The relationship between memory attention and the limits of what human minds can retain remains an intriguing and not fully mapped territory. The double-slit experiment reveals something deeply strange about reality. In one of the most famous experiments in all of physics, a stream of particles is fired at a barrier with two slits in it, and what lands on a screen behind it is recorded. When both slits are open, an interference pattern appears on the screen, bands of light and dark that are characteristic of waves, not particles. This already seems odd, but here is the strange part. When detectors are placed at the slits to observe which slit each particle passes through, the interference pattern disappears. Simply observing the particles seems to change their behavior. They stop behaving like waves and start behaving like particles. What this means about the nature of observation, about whether particles have definite properties before they are measured, and about the relationship between the act of measurement and physical reality has been debated for a century without resolution. The double-slit experiment works exactly as quantum mechanics predicts, but what it means about the nature of reality itself is still one of the deepest open questions in all of physics. We do not understand the long-term stability of the solar system. The solar system has existed for about 4.5 billion years, and the planets seem to have maintained their roughly stable orbits throughout that time. But when mathematicians apply the laws of Newtonian gravity and general relativity to simulate the solar system's behavior over very long timescales, they find that the system is not entirely stable in the mathematical sense. It is what is called chaotic, meaning that tiny uncertainties in the current positions and velocities of the planets grow exponentially over time, making long-term predictions impossible. Simulations show that over billions of years, there is a small but non-negligible probability that Mercury's orbit could become so eccentric that it might eventually collide with Venus or be ejected from the solar system entirely. How likely this is, and on what timescale, remains uncertain. The solar system looks stable, but beneath that stability lies a deep mathematical uncertainty. We cannot fully explain why humans are the only animal with cumulative culture. Many animals learn from one another. Chimpanzees pass along tool use behaviors. Dolphins teach hunting techniques. Birds learn songs from parents and neighbors. But only humans have cumulative culture, a culture that builds on itself over time, where each generation inherits and improves on the knowledge of the previous one. Our technology today is the result of thousands of years of accumulated invention and refinement each generation, standing on the shoulders of those before. No other animal does this in the same way. Why not? What is it about the human mind that allows this kind of cultural ratchet where knowledge builds rather than being lost and rediscovered each generation. We have hypotheses involving language, the ability to teach explicitly theory of mind and other cognitive capacities, but the full explanation of why cumulative culture is uniquely human remains an open question. In evolutionary biology and cognitive science, certain mathematical structures seem to describe the universe perfectly, and nobody knows why. In the early 20th century, the physicist Eugene Wigner wrote an essay titled "The Unreasonable Effectiveness of Mathematics in the Natural Sciences." His point was this: mathematicians often develop abstract structures for purely theoretical reasons with no reference to the physical world at all, and then sometimes decades or centuries later, those abstract structures turn out to perfectly describe some newly discovered aspect of physical reality. Non-Euclidean geometry was developed as a mathematical curiosity and later turned out to be exactly the structure needed to describe space-time in Einstein's theory of general relativity. Complex numbers were invented to solve abstract equations and turned out to be fundamental to quantum mechanics. Why should the universe follow mathematical rules at all? Why should the structures that mathematicians invent for purely logical reasons so often match the structures of physical reality? This question has no accepted answer, and it sits at the boundary between mathematics, physics, and philosophy. We still do not know what caused the Cambrian explosion. About 540 million years ago, in a geological period called the Cambrian, something extraordinary happened. In a geologically very short span of time, most of the major animal body plans that exist today appeared in the fossil record. The diversity of multicellular life exploded. Rays appeared. Skeletons appeared. Complex nervous systems, jointed limbs, and entirely new ecological relationships all seem to emerge in what is on the geological timescale almost the blink of an eye. This is called the Cambrian explosion. And why it happened when it did, what triggered this sudden diversification after billions of years of much simpler life, is still debated. Possible factors include changes in ocean chemistry, increases in oxygen levels, ecological dynamics, genetic regulatory innovations, or some combination. No single explanation has been accepted as complete. We do not understand the mechanism of high-temperature superconductivity. Superconductivity is a phenomenon where certain materials, when cooled to very low temperatures, lose all electrical resistance. Current can flow through them without losing any energy at all. This was discovered in the early 20th century and was eventually explained by a theory called BCS theory. But in the late 1980s, researchers discovered materials that became superconducting at much higher temperatures than BCS theory could explain. These high-temperature superconductors have been studied intensively for nearly 4 decades, and despite enormous theoretical effort, no consensus explanation of the mechanism behind them has been reached. Understanding high-temperature superconductivity could have profound practical implications, potentially enabling lossless electrical grids and other transformative technologies. The mechanism remains an open problem. We do not know why humans alone among primates lack fur. Most mammals have fur. Our closest relatives, chimpanzees, gorillas, and bonobos, are covered with it. Humans are almost entirely naked by comparison, and this is genuinely unusual. Various hypotheses have been proposed that hairlessness helped our ancestors stay cool while running long distances on the African savanna, that it reduced parasites, that it was related to sexual selection. All of these explanations have some plausibility, and none has been definitively confirmed. The genetic changes that lead to human hairlessness have been identified to some degree, but the evolutionary pressures that drove those changes, why nakedness was advantageous enough to spread through the population, is something we are still working out. The nature of quantum measurement is still debated. In quantum mechanics, a particle can exist in a superposition, a state that is in some sense multiple possibilities at once. When you measure it, you get a definite answer. The wave function, as it is called, appears to collapse from many possibilities to one outcome. But the process of this collapse, what actually happens during measurement, and why measurement produces a definite result, is the subject of one of the deepest and longest-running debates in physics. Different interpretations of quantum mechanics propose radically different answers. The Copenhagen interpretation says the wave function collapse is just something that happens upon measurement and does not need further explanation. The many worlds interpretation says all outcomes occur and the universe branches at each measurement. Other interpretations invoke hidden variables, pilot waves, or information theoretic frameworks. The mathematics of quantum mechanics is extraordinarily precise. What the mathematics means about the nature of reality is still genuinely unsettled. We do not know why we are compelled to tell stories. Humans are storytelling animals. We tell stories in every culture, in every period of history, in every corner of the world. We tell them around fires and books and films and dreams, in the quiet retellings of our days to the people we love. We cannot seem to help it. Narratives are how we understand the world, how we share experience, how we make meaning out of the raw material of events. But why the mind is structured this way, why it reaches for story rather than some other form of cognition, is not entirely understood. There are theories that narrative thinking helped our ancestors model the intentions of other people, or that storytelling strengthened social bonds, or that it was a way of rehearsing and sharing knowledge. But the deep reason why story is so fundamental to human psychology remains more of an open question than a solved one. We cannot explain the specific patterns of snowflakes. Every snowflake is different. This is a cliché you may have heard many times, but the underlying mystery is less often discussed. Snow crystals grow as water vapor deposits on a tiny nucleus, usually a dust particle, as it falls through the atmosphere. The crystal grows symmetrically because all 6 branches develop under essentially the same conditions at any given moment in the snowflake's fall. But the exact path through the atmosphere, the tiny variations in temperature and humidity that each snowflake encounters on its journey to the ground are unique. So the crystal records its own journey in its structure, no 2 paths ever identical. We understand the physics of crystal growth well enough to explain the basic hexagonal symmetry of snowflakes, but the precise prediction of what pattern a given snowflake will form given a specific path through specific atmospheric conditions remains beyond our current ability. The snowflake is a product of chaos made beautiful, and its specificity is in a sense uncomputable. How the brain recognizes faces is not fully understood. Human beings are extraordinarily good at recognizing faces. We can identify a familiar face in a fraction of a second, often from partial or degraded images, and we can distinguish between tens of thousands of different people by face alone. This ability is so refined that it represents one of the most impressive feats of visual processing in the animal kingdom. The brain dedicates specific regions, including the fusiform face area, to face processing. But the precise mechanisms by which the brain represents, stores, and retrieves facial information, and why some people are much better at this than others, and why some people have prosopagnosia, a condition that makes face recognition impossible, are not fully understood. Face perception sits at the intersection of vision memory and social cognition in ways that are still being mapped. Some people can hear colors and taste sounds, and we do not fully understand why. Synesthesia is a neurological phenomenon where one sensory experience triggers an additional sensory experience. Some synesthetes hear a specific musical note and simultaneously see a particular color. Others taste shapes or feel textures in response to sounds or see numbers and letters as inherently colored. Synesthesia is not metaphorical. The additional perceptions are real, consistent, and involuntary. Someone who sees the no 5 is red will always see it as red, not sometimes blue or green. Synesthesia runs in families and appears to be related to differences in neural connectivity, but the full explanation of why some brains make these cross-sensory connections and others do not, and what exactly is happening at the neurological level when a sound produces a color experience. remains an area of ongoing research. We cannot explain why certain animals have such long lifespans. The Greenland shark lives for hundreds of years. Some individuals may be nearly 500 years old. Ocean quadog clams have been found to live past 500 years. The bowhead whale regularly lives past 200. Certain tortoises, naked mole rats, and even some trees live for extraordinary lengths of time compared to their body size or metabolic rate. Understanding why certain organisms live so much longer than others, and what mechanisms allow them to resist aging and cellular damage over such extreme timescales is one of the most active and medically relevant research areas in biology today. The insights gained from these long-lived animals could potentially transform our understanding of human aging, but the complete picture of why lifespans vary so dramatically and what the fundamental limits of biological aging actually are remains unknown. The solution to turbulence is one of the great unsolved problems in mathematics. Turbulence is what you see when you swirl cream into coffee and watch it spread in unpredictable spirals and eddies. It's what happens in the atmosphere when air moves chaotically. It is the bumpiness of flights through rough air. Despite being something we encounter constantly, the mathematical description of turbulence is one of the famous millennium prize problems, a list of 7 unsolved mathematical questions for which the Clay Mathematics Institute has offered a prize of $1 million each. Whether the equations that govern fluid flow, called the Navier-Stokes equations, always have well-behaved solutions, or whether they can produce situations where quantities like velocity become infinite in finite time is a question that remains open. Turbulence is everywhere, and at the deepest mathematical level, we do not yet understand it. We do not know what determines the timing of puberty, the onset of puberty, the biological transition from childhood to sexual maturity is one of the most significant events in human development. It is controlled by a complex cascade of hormonal signals beginning in the brain. The timing varies considerably between individuals and has been shifting over the past century, with puberty beginning earlier on average in many populations. The factors responsible for this shift, which may include nutrition exposure to environmental chemicals, levels of stress, and body composition, are still being studied. The genetic regulation of puberty timing is complex, involving many different genes and what exactly triggers the brain to initiate the hormonal cascade at the particular moment it does. The mechanism of the onset of puberty itself is not completely understood. We do not fully understand why some materials are magnetic and others are not. Magnets are things most of us encounter every day. They hold notes to refrigerators. They drive electric motors. They store data on hard drives. But why certain materials are magnetic is actually a more subtle question than it might appear. The magnetism of iron in similar materials arises from the quantum mechanical spin of electrons, and then way these spins align across large regions of the material called magnetic domains. But the precise rules that determine why some materials support this alignment and others do not, why some are ferromagnetic and others are not, involves complex quantum mechanical interactions that are still an active area of condensed matter physics. The full theory of magnetism in complex materials is not yet complete. We cannot explain déjà vu. Most people have experienced déjà vu, a peculiar sensation of feeling certain that you have experienced a present moment before, even though you know rationally that you have not. It is brief, usually lasting only seconds, and it fades almost as quickly as it arrives. Despite its universality, the neurological mechanism behind déjà vu has not been definitively identified. Various hypotheses exist that it involves a mismatch between memory storage and retrieval processes, that it results from a brief asynchrony between what the brain perceives and what it registers as familiar, that it is related to the same processes that generate false memories. Some neuroscientists believe it involves the temporal lobes and the hippocampus, but no single explanation has been confirmed, and the fact that déjà vu is so common yet so fleeting makes it difficult to study systematically. The deep ocean remains largely unexplored, and full of unknown life. Despite covering more than 70% of the Earth's surface, the ocean remains our most poorly understood environment. The deep sea below 200 meters is almost entirely unexplored in any systematic way. We have better maps of the surface of Mars than we do of the ocean floor. Entire mountain ranges lie beneath the water range is larger than the Himalayas that have never been seen by human eyes. Vast plains of sediment stretch across the abyssal zone, broken by volcanic ridges and deep trenches that plunge to depths of nearly 11 kilometers. The Mariana Trench alone is deeper than Mount Everest is tall, and it has been visited by humans fewer times than the surface of the moon. The life found in the deep ocean continues to surprise researchers. With every expedition, new species are regularly discovered, many with features and behaviors that challenge existing biological understanding. Bioluminescent creatures, organisms that survive without any sunlight, animals adapted to crushing pressures and near freezing temperatures. The deep ocean is an entire alien world that exists on our own planet. Species like the giant squid were considered mythological for centuries before physical evidence confirmed their existence. Discoveries in recent decades have included fish with transparent heads, jellyfish the size of garbage bins, and ecosystems clustered around hydrothermal vents that derive all their energy from chemistry rather than sunlight. How many species remain undiscovered, and what they might reveal about the limits and possibilities of life is genuinely unknown. Deep ocean may be the largest inhabited space on Earth that humans have never mapped. We do not understand why we blush. Blushing, the reddening of the face in response to embarrassment or social attention, is a uniquely human phenomenon. Other animals do not blush. It is involuntary, which makes it interesting because it communicates something genuine about our internal state that we cannot suppress or control. But why humans evolved this response, what advantage it confers, has never been satisfactorily explained. One idea is that blushing signals to others that you are aware you have made a social misstep, which may have functioned to repair social bonds or signal honesty. Another possibility is that it is a byproduct of the body's stress response with no specific adaptive purpose. Charles Darwin himself was fascinated by blushing and wrote about it extensively. Even he could not arrive at a satisfying explanation for why it evolved. More than a century and a half later, the question remains open. We cannot explain the mystery of the placenta. The placenta is one of the most extraordinary organs in the mammalian body. It forms during pregnancy, connecting the developing fetus to the mother's blood supply, while preventing the mother's immune system from attacking the fetus as foreign tissue. This is immunologically remarkable because the fetus carries the father's genes and is in a very real sense partly foreign to the mother's body. How the placenta achieves this immunological tolerance, how it regulates the exchange of nutrients and gases between two beings with distinct immune systems, and how it knows when to trigger labor at the appropriate time are questions that reproductive biology is still working to answer. The placenta does something the rest of the body cannot do anywhere else, and the full story of how it does it is incomplete. We do not understand how the brain learns language in infancy. Human infant enters the world with no language within a few years, with no formal instruction. Simply by being immersed in an environment where language is used, the child has acquired a complete working knowledge of at least one language, including its grammar, its sounds, its vocabulary, and the subtle social rules of its use. It happens faster and more effortlessly than any second language learner experiences, and the question of how remains genuinely open. The linguist Noam Chomsky proposed that humans are born with an innate language acquisition device, a built-in biological capacity for language. But what this capacity consists of at the neurological level, how the infant brain extracts the rules of language from raw experience, and why this capacity seems to diminish after a critical period in early childhood, are questions that language researchers have been working on for decades without complete answers. The mechanism of evolution itself has open questions. Natural selection is one of the most powerful and well-confirmed ideas in all of science. Its basic logic that heritable variations in traits affect survival and reproduction, and that advantageous traits tend to spread through populations over time is supported by overwhelming evidence from genetics, the fossil record, and direct observation. But the mechanisms of evolutionary change are not exhausted by natural selection alone, and some of the details remain active areas of debate. The relative importance of gradual change versus sudden shifts, the role of neutral evolution, where changes spread without being particularly helpful or harmful, the contribution of developmental constraints to the myths, direction of evolutionary change, the possibility of inherited epigenetic changes that do not involve changes to DNA sequence. These are all areas where evolutionary biology is still actively developing. The basic fact of evolution is not in question. The full complexity of its mechanisms is still being mapped. We do not know what causes certain people to have perfect pitch. Absolute pitch, often called perfect pitch, is the ability to identify or produce any musical note without a reference tone. A person with perfect pitch can hear any sound and name the note it corresponds to, or produce any requested note without hearing one first. It is relatively rare, occurring in perhaps 1 in 10,000 people in Western populations and considerably more common in those who grew up learning tonal languages or received musical training before the age of 7. The ability has a genetic component, runs in families, and is associated with certain structural features of the brain. But why some people have it and others do not, and what the complete developmental story of its acquisition is, remains unclear. It appears to involve a critical period in early childhood, but the biological details of what makes some brains able to develop this capacity and others unable to are still being studied. The longevity of certain viruses is not fully understood. The variola virus, which caused smallpox, killed hundreds of millions of people throughout history and was one of the most feared diseases ever known. It was eradicated through vaccination, one of the greatest public health achievements of the 20th century. And yet smallpox viruses still exist preserved in secure laboratory facilities. The fact that viruses can survive storage for extraordinarily long periods, that ancient viruses can be reconstructed from genetic information preserved in ice cores or permafrost, and the dormant viral sequences exist within the human genome itself, are aspects of viral biology that have profound and not fully understood implications. How viruses persist across time, how they interact with host genomes, and what the ancient viral sequences embedded in our own DNA are actually doing there are questions that virology continues to explore. Why humans have a sense of humor is not fully explained. Laughter is universal. Every human culture has humor. We find things funny from infancy. The ability to appreciate and create jokes defined incongruity, amusing to share the release of laughter with others, seems to be a fundamental feature of what it means to be human. But why humor evolved what it does for us biologically and socially, and why it feels as good as it does, is not completely understood. Humor seems to involve a kind of cognitive surprise, a moment when an expectation is violated, in a way that is benign or inconsequential. It has been proposed that humor may have evolved to signal intelligence, to strengthen social bonds, or to help us process and diffuse potentially threatening situations by recognizing them as harmless. These hypotheses have some support, but the full evolutionary and psychological account of humor is still being developed. The formation of continents is not entirely understood. The Earth's surface is divided into plates of rock that move very slowly over time, driven by convection in the hot mantle beneath. This is the theory of plate tectonics, one of the great unifying discoveries of 20th century geology. But certain aspects of how Earth's crust formed and evolved, particularly in the very early history of the planet, remain uncertain. The timing and mechanism by which the first continental crust formed, how plate tectonics itself that started on early Earth, and why Earth has plate tectonics while other rocky planets like Venus and Mars do not are all active research questions. The early history of the Earth's surface is partly hidden by billions of years of subsequent geological change, making it one of the harder puzzles in planetary science. We cannot explain why humans are the only species that cooks food. Fire and cooking changed everything. The application of heat to food breaks down fibers, kills pathogens, and makes nutrients more easily digestible. Some researchers, most notably Richard Wrangham, have argued that cooking was not merely convenient, but transformative, that it fundamentally altered human evolution by enabling us to extract more energy from food, potentially helping to fuel the expansion of our large and metabolically expensive brains. But the origin of cooking, when our ancestors first began using fire to prepare food, and why this habit became universal while no other animal has adopted, it is still debated. The evidence for fire use extends back hundreds of thousands of years, but the details of when cooking specifically began as opposed to incidental contact with fire and what it meant for human biology and society are still being worked out. The nature of time in quantum mechanics is deeply unclear. In our everyday experience, time is a parameter, something that flows from past to future, carrying events along with it. In Einstein's general relativity, time becomes part of space-time, affected by gravity and motion, but still a fundamental dimension of reality. But when physicists try to formulate a quantum theory of gravity, time becomes deeply problematic. In the Wheeler-DeWitt equation, one of the early attempts to combine general relativity and quantum mechanics, time simply disappears from the equation entirely. What this means for reality, whether time is fundamental or emergent, and what a physics without time would actually look like, is one of the most challenging and least resolved questions. At the frontier of theoretical physics, we cannot fully explain how birds know which direction to migrate. Migration is one of nature's most astonishing achievements. Arctic terns travel from the Arctic to the Antarctic and back again every year, a round trip of roughly 70,000 kilometers. Many species navigate to the same specific locations year after year, guided by a combination of the sun, the stars, Earth's magnetic field, landmarks, and possibly even smell. But the integration of all these cues, how a bird's nervous system combines multiple streams of information to produce reliable navigation across thousands of miles, is not completely understood. The magnetic sense in particular involves quantum processes in the eye that are still being characterized. The full navigation system of a migratory bird is a remarkable piece of biological engineering whose details are still being mapped. The trigger for the formation of tornadoes is not always predictable. Meteorology has made extraordinary advances in understanding and predicting weather, but tornado formation remains one of the most difficult challenges in atmospheric science. We know that tornadoes form from severe thunderstorms, particularly supercell thunderstorms, and we understand the general conditions that make tornado formation more likely. But why a specific supercell produces a tornado and another equally severe supercell does not? What the precise tipping point is still not fully understood. Storm chasers and researchers use sophisticated instruments to study tornado formation up close, and computational models have improved considerably. But the final step, the conditions that tip a severe storm into tornado production, involves very small-scale atmospheric dynamics that remain difficult to observe and model. We do not know how some people can enter extremely cold water without apparent harm. The Dutch athlete Wim Hof has demonstrated an ability to endure extreme cold temperatures that should, by all conventional physiological understanding, be life-threatening. He has climbed near the summit of Mount Everest wearing only shorts. He has swung under ice. He attributes these abilities to a breathing and meditation technique, and studies of his physiology have produced genuinely surprising results, including evidence of voluntary influence over autonomic processes like inflammation that were previously thought to be entirely outside conscious control. How these techniques work at a physiological level and the extent to which they can be taught to others is still being studied. The implications for our understanding of the relationship between mind and body are significant and not fully worked out. The mechanism of the immune system's memory is not completely understood. When you receive a vaccination or recover from an infection, your immune system learns. It produces memory cells that can recognize the pathogen if it returns, enabling a faster and more powerful response. This immune memory can last for decades, and in some cases for an entire lifetime. How exactly these memory cells persist for so long, how they maintain their readiness over years without constant stimulation, and what determines how long immune memory lasts for different pathogens and vaccines, are questions that immunology is still working to answer. Understanding immune memory better is crucial for designing more effective vaccines and for understanding autoimmune conditions, and significant work remains to be done. We do not fully understand the role of junk DNA. For decades after the structure of DNA was determined, scientists believed that the vast majority of the human genome, perhaps 97 of it, served no function. It was dismissed as junk DNA sequences that appeared to code for nothing and were assumed to be evolutionary debris. But large-scale genomic projects, particularly the ENCODE project, have revealed that much of this supposed junk is transcribed into RNA and may play regulatory roles, influencing how genes are turned on and off. The full scope of what non-coding DNA actually does, how much of it is functional, and what its functions are remains an active area of research. The genome is far more complex than early models suggested, and we are still in the early stages of understanding what all of it does. The origin of the moon has uncertainties. The most widely accepted theory for the moon's origin is the giant impact hypothesis that roughly 4.5 billion years ago, a body approximately the size of Mars collided with the early Earth, and the debris from this collision eventually coalesced into the moon. This theory accounts for many features of the Earth-Moon system, including the moon's relatively small iron core and the similar isotopic compositions of Earth and moon rocks. But it also has difficulties. Recent analysis suggests the moon's composition resembles Earth's more closely than the giant impact models would predict. The details of the collision, its angle, the size of the impactor, and what happened to the material afterward are still being refined. The story of how the moon came to be is largely understood, but the complete picture has not yet fully settled. We cannot fully explain why art matters to people. Humans make and experience art across every culture that has ever been documented. Cave paintings tens of thousands of years old show that artistic expression appeared very early in human prehistory. Music, visual art, dance, storytelling. They are not luxuries that appear only after basic needs are met. They seem to be fundamental to human life in a way that is difficult to account for purely in terms of survival advantage. Why art moves us, why beauty affects us the way it does, what the experience of aesthetic emotion actually is at the neurological level, and what evolutionary pressures shaped our capacity for artistic response are questions that sit at the intersection of neuroscience, evolutionary biology, psychology, and philosophy. They are questions with many proposed answers and no complete consensus. The protein folding problem was partially solved, but mysteries remain. Proteins are the working molecules of life chains of amino acids that fold into specific three-dimensional shapes that determine their function. For decades, predicting how a protein would fold from its amino acid sequence was one of the grand challenges of biology. In 2020, an artificial intelligence system called AlphaFold made transformative progress on this problem, predicting protein structures with remarkable accuracy. But this is not the end of the story. How proteins fold so quickly in the cell, avoiding the vast number of incorrect configurations they could adopt, is still not fully understood. How proteins interact with one another in the crowded environment of a living cell, and how this relates to diseases where proteins misfold, such as Alzheimer's disease, are still areas of active research. We do not understand why childhood memories are so rarely retained. Ask most adults for their earliest clear memory, and they will typically struggle to recall anything from before the age of 3 or 4. This phenomenon is called infantile amnesia, and it is one of the more curious features of human memory. Children in their first few years of life are clearly capable of learning and remembering things in the short term. They recognize faces, learn words, form attachments, and yet almost none of this early experience leaves accessible long-term memories that persist into adulthood. Why the brain fails to consolidate early childhood experiences into lasting, autobiographical memories is still not fully understood. It may relate to the immaturity of the hippocampus in infancy, or to the development of language as a framework for encoding memories, or to other factors. The question of where our earlier selves went, why those first years of experience leave so little accessible trace, is one that memory researchers are still exploring. The cause of ice ages is still being refined. Ice ages, the periods when ice sheets expand dramatically to cover large portions of the continents, have occurred repeatedly throughout Earth's history. The major driver of ice age cycles appears to be variations in Earth's orbit and axial tilt called Milankovitch cycles, which alter how much sunlight reaches different parts of the Earth at different times of year. But these orbital changes alone are not sufficient to explain the full magnitude of the glacial cycles or their timing. Feedback mechanisms involving carbon dioxide, ocean circulation, ice sheet dynamics, and other factors amplify the orbital signals. The precise interplay of these feedbacks and why ice ages have occurred, the intervals they have, and with the intensity they have, is still the subject of active research. In paleoclimatology, the aging of the brain is not completely understood. As the brain ages, certain cognitive abilities decline. Processing speed slows, working memory becomes less efficient, the risk of neurodegenerative diseases like Alzheimer's increases. But why the brain ages the way it does, what the fundamental biological processes are that underlie cognitive decline, and why some people maintain sharp cognition into very advanced age, while others experience significant decline, is still not fully understood. The accumulation of protein aggregates like amyloid plaques and tau tangles is clearly involved in Alzheimer's disease, but whether these are causes or consequences of the disease, and what triggers the process to begin, remains an active debate. The biology of brain aging is a major research priority, and many questions remain open. We cannot fully explain why humans form lasting romantic pair bonds. Most mammal species are not monogamous. Humans show a tendency, by no means universal, toward something like long-term pair bonding, a tendency that is far less common among our primate relatives. What drives this tendency? What biological mechanisms support long-term attachment between partners, and how these mechanisms evolved is a question that evolutionary biology, neuroscience, and anthropology all approach from different angles. Hormones like oxytocin and vasopressin play a role in attachment. Cultural and social factors clearly influence relationship structures, but the complete picture of how human pair bonding evolved and what sustains it biologically is not yet fully drawn. Love, in all its varieties, remains partly beyond the reach of any single scientific explanation. Quantum tunneling in biology may be widespread and is not fully understood. Quantum tunneling is a phenomenon where a particle passes through a barrier that it classically should not be able to cross. It occurs because at quantum scales, particles exist as probability distributions rather than precise locations, and there is a finite probability of finding the particle on the other side of any barrier. This is fundamental to the operation of tunnel diodes in electronics and to nuclear fusion in the sun. And there is growing evidence that quantum tunneling occurs within living cells, contributing to processes like enzyme catalysis, DNA mutation, and photosynthesis. The role of quantum effects in biological systems is an emerging field called quantum biology, and many of its central questions about how quantum phenomena influence chemistry in the warm, wet, complex environment of a living cell are still being answered. We do not know how the brain produces creative insight. You are working on a problem and getting nowhere. You set it aside. Then sometimes in the shower, or on the edge of sleep, or in the middle of doing something completely unrelated, the answer arrives. Sudden sense of clarity, the pieces fitting together. This is the experience of insight, the creative leap. Neuroscientists have studied insight by giving people puzzles that have a sudden solution and watching what happens in the brain at the moment of realization. There is typically a burst of gamma wave activity in the right anterior temporal lobe. But what this represents how the brain moves from searching to sudden solution, and what happens during the period of incubation when the mind seems to work on problems below conscious awareness, is still not fully understood. Creativity itself in all its forms is one of the most deeply personal and least scientifically charted territories of the human mind. The behavior of prime numbers defies complete explanation. Prime numbers, those divisible only by 1 and themselves, have been studied for thousands of years. They are the atoms of arithmetic, the building blocks from which all other whole numbers are constructed, and their distribution along the number line has a quality of deep mystery. The Riemann hypothesis, one of the most famous and important unsolved problems in mathematics, concerns the distribution of primes and has been open for more than a century and a half. Proving or disproving, it is worth $1 million through the Millennium Prize. Despite all that mathematicians have learned about primes, why they are distributed the way they are, whether there are patterns hidden in the primes that we have not yet seen, and how their spacing relates to the behavior of a function called the Riemann zeta function, remain among the deepest open questions in all of mathematics. We do not fully understand the origin of handedness in animals. It is not just humans who show lateralization. Many animals show a preference for one side over the other. Cats tend to prefer a front paw for reaching. Chimpanzees show handedness at the population level. Parrots favor one foot. Even some invertebrates show lateralized behavior. And the origin of this bias, why evolution produced brains and nervous systems that process the world asymmetrically, is not fully understood. In humans, language is typically localized to the left hemisphere, and most people are right-handed. The connection between brain asymmetry and handedness is clear, but complex. Why asymmetric brain organization evolved, and what advantages it confers, is still an active area of research. The size of the universe beyond the observable is unknown. The observable universe is the region of space from which light has had time to reach us since the Big Bang. This is a sphere approximately 93 billion light-years in diameter, but the universe almost certainly extends far beyond this. In most cosmological models, it extends enormously, further, possibly infinitely. We have no way of observing what lies beyond the observable horizon. The universe could be many times larger than what we can see, or it could be infinite. It could be finite, but unbounded, curving back on itself, like the surface of a sphere in higher dimensions, or it could have a particular topology we have not yet inferred from the data. The true size and shape of the whole universe, beyond what we can observe, is simply not known. We do not understand why some people are natural polyglots. Some people acquire new languages with remarkable ease. Give them a few months of immersion, and they are conversational. Give them a few years, and they may be indistinguishable from a native speaker. Others struggle enormously with second languages even after years of study. What underlies this difference in language learning ability is not fully understood. It involves a mix of factors: the efficiency of auditory processing, working memory, phonological awareness, and possibly the structure of neural networks involved in language. But no single predictor reliably identifies who will become a natural language learner and who will not. The diversity in human linguistic ability, from those who speak many languages effortlessly to those for whom even one second language is a profound challenge, is a genuinely interesting and not fully explained aspect of human cognitive variation. The coloration of certain animals cannot be fully explained by evolution. The peacock's tail is one of the most famous puzzles in evolutionary biology. It is enormous, heavy, and makes the bird more visible to predators. By any measure of simple survival, it should not exist. Darwin himself found it troubling. The explanation that has gained the most acceptance is sexual selection. The idea that peahens prefer males with more elaborate tails, making the trait advantageous for reproduction, even if it is costly for survival. But exactly what information the tail communicates, whether it honestly signals the male's overall genetic quality, and why the particular aesthetic preferences of peahens evolved in the way they did, is still a subject of active research and debate. More broadly, the question of why biological beauty is so widespread and so elaborate is one that evolutionary biology continues to explore. We cannot fully explain the long-term storage of traumatic memories. Traumatic memories can persist for decades with unusual vividness and persistence. Unlike ordinary memories, which tend to fade and change over time, traumatic memories often remain sharp and can be triggered by sensory cues returning with a force that does not diminish in the way other memories do. The neurological mechanisms underlying traumatic memory storage differ from ordinary memory consolidation in ways that are still being understood. The amygdala, which processes emotional significance, appears to play a larger role. The precise changes in neural circuitry that make some memories so persistent and intrusive, and what this means for treating conditions like post-traumatic stress is an area of intense ongoing research with many open questions. The cognitive abilities of plants are a growing mystery. Plants do not have nervous systems. They have no neurons, no brains. And yet research over the past few decades has revealed that plants respond to their environments in ways that look surprisingly like cognition. They can sense the direction of light, the presence of nearby competitors, the chemistry of the soil. Some species appear to warn neighboring plants of insect attack through chemical signals. Certain plants seem to remember and learn in simple ways, adjusting their responses to repeated stimuli. How plants achieve these behaviors without anything resembling a nervous system, and what the mechanisms are that allow for something like information processing and adaptive response in the absence of neurons is a genuinely open and sometimes controversial area of biology. The boundaries of cognition may be wider than we thought. We do not know why certain foods become universally loved. Sweetness, fat, and saltiness are reliably preferred across human cultures, likely because they indicate caloric density and minerals that were valuable to our ancestors. But beyond these basics, certain specific foods have become beloved across many different cultures and contexts in ways that are not fully explained. The comfort that people derive from certain foods, the way smells and tastes can trigger powerful emotional memories. The cross-cultural appeal of specific flavor combinations are aspects of human food preference that involve psychology, memory, culture, and biology in ways that are still being mapped. The science of taste and food preference is far more complex than it might appear, and our understanding of why we love what we love is incomplete. The long-term fate of intelligence in the universe is unknown. Intelligence, as we know, it requires structure, organized matter-energy gradients, complex systems capable of processing information. The universe is currently in an era that supports all of these things. Stars burn, planets form, life evolves, minds emerge, but the universe is also aging. Given a long enough timescale, stars will exhaust their fuel, black holes will eventually evaporate through Hawking radiation. The universe will tend toward maximum entropy, a state of uniform temperature with no available energy gradients. What this means for intelligence in the very long run. Whether intelligence could find ways to persist as the universe cools and darkens, or whether the emergence of mind is necessarily a temporary feature of a young and energetic universe, is a question that sits at the intersection of physics, cosmology, and philosophy, and has no settled answer. We do not fully understand the sense of smell. Smell is the most ancient of the senses, deeply connected to memory and emotion in ways that the other senses are not. Smell can return you instantly to a moment decades in the past with a vividness that visual or auditory memories rarely match. But the neuroscience of smell is in many ways less well understood than vision or hearing. The olfactory system connects directly to the amygdala and hippocampus without the thalamic relay that other senses use, which may explain its powerful connection to emotion and memory. But how the brain identifies and categorizes the enormous range of molecules that constitute different smells, and how it creates the subjective experience of a particular scent from chemical signals involves questions that olfactory neuroscience is still working to answer. The genetic basis of complex traits is not fully mapped. Height is a simple example. It is clearly heritable, running strongly in families, but the hundreds of genetic variants associated with height each contribute only a tiny fraction of its heritability. When you add up all the known genetic contributions, they still do not fully account for the observed heritability of height. This gap is called the missing heritability problem, and it applies to many complex traits and diseases. Intelligence, personality, susceptibility to various diseases. The genetics of complex human characteristics involves a web of interactions between many genes and between genes and environment, and our ability to fully account for heritability from known genetic variants remains limited. The architecture of complex traits in the human genome is richer and more complicated than early genomics hoped. We cannot explain certain mathematical coincidences in mathematics. Certain numerical coincidences show up across entirely unrelated areas with no apparent explanation. The fine structure constant, a fundamental constant of physics describing the strength of the electromagnetic interaction, has a value close to 1/137th. This number appears across different physical contexts in ways that some physicists have found suggestive of a deeper pattern, though no one has been able to identify what that pattern is. Certain other numerical relationships across physics and mathematics appear to be coincidences, but feel too precise to be accidental. Whether these are genuine deep connections waiting to be understood, or simply the result of human pattern seeking in data that is not actually meaningfully connected, is something that neither mathematics nor physics has yet resolved. The mechanism of pain is not fully understood. Pain is one of the most immediate and compelling experiences in human life. It is protective, warning us of tissue damage and prompting us to withdraw from harm. But the experience of pain is far more complex than a simple alarm system. Phantom limb pain, where people experience pain in limbs they no longer have, demonstrates that pain can exist entirely without tissue damage. Chronic pain, which persists long after an injury is healed, shows that pain is not simply a readout of damage. The way pain is modulated by attention, by emotional state, by expectation, and by the social context in which it occurs reveals that pain is constructed by the brain in ways that go far beyond simple signal transmission from injury sites. Understanding pain fully enough to treat it effectively, particularly chronic pain, is one of the most important and still incompletely solved challenges in medicine. We do not know what caused the Bronze Age collapse around 12 BCE. Within the space of a few decades, virtually every major civilization in the Eastern Mediterranean collapsed. The Egyptian New Kingdom was severely weakened. The Hittite Empire disappeared entirely. Mycenaean Greece collapsed, its palace culture vanishing. The city of Outgrit on the Syrian coast was destroyed and never rebuilt. Trade networks that had connected the region for centuries fell apart. The cause of this Bronze Age collapse, one of the most traumatic civilizational breakdowns in history, is genuinely uncertain. Archaeological evidence suggests a combination of factors: drought, invasion by the mysterious Sea People's internal rebellion systems, collapse as complex interconnected societies became fragile under simultaneous stresses. But the precise sequence of events and which factors were primary is still debated by historians and archaeologists. We cannot explain why humans have such long childhoods. Humans have the longest period of juvenile dependence of any primate. Children require intensive care for many years before becoming self-sufficient, and humans do not reach full adulthood until their mid-20s, when the prefrontal cortex finally completes its development. This is an extraordinarily long investment by parents, and by any measure of evolutionary efficiency, it is costly. The most compelling explanation is that human brains are so complex that they require a very long period of development, learning, and social embedding before they can operate fully. The extended childhood is the price of cognitive complexity, but the details of why the human developmental timeline is as long as it is and what specifically happens during those years that could not be compressed are not fully understood. The way general relativity and quantum mechanics relate is unknown. This is perhaps the deepest problem in all of fundamental physics. General relativity. Einstein's theory of gravity describes the universe at large scales with extraordinary accuracy. Quantum mechanics describes the behavior of matter and energy at the smallest scales with equal accuracy. Both theories are among the most successful in the history of science, and they are fundamentally incompatible with each other. When you try to apply both simultaneously to describe gravity at quantum scales, you get nonsensical infinities. Search for a theory of quantum gravity, a framework that encompasses both relativity and quantum mechanics in a consistent way, is the deepest open problem in theoretical physics. String theory and loop quantum gravity are among the approaches being explored, but none has yet been confirmed by experiment or accepted as the answer. We cannot fully explain the placebo effect on surgery. The placebo effect in pill taking is surprising enough, but perhaps even more remarkable is the evidence for placebo effects in surgery. In studies where patients received either real surgical procedures or sham surgeries, where they were given anesthesia and an incision, but the actual procedure was not performed, patients in both groups often showed significant improvement. Studies of this kind have been conducted for conditions, including knee surgery for arthritis and certain procedures for back pain, with results that have challenged assumptions about when and why surgery works. The idea that a surgical procedure can produce benefit through mechanisms other than the mechanical effect of the procedure itself raises profound questions about what the body is doing and how expectation and ritual affect healing. The implications are still being debated. In medicine, we do not know what dark energy will do to the universe over time. The accelerating expansion of the universe, driven by dark energy, appears to be constant at present, but physicists do not know whether it will remain constant. If dark energy increases over time, the expansion of the universe will accelerate more and more dramatically, eventually pulling apart galaxies, then solar systems, then planets, then atoms, themselves in a scenario called the Big Rip. If dark energy decreases, expansion might slow, stop, or even reverse, potentially leading to a big crunch where the universe collapses back on itself, or the expansion might continue at a steady rate forever. Which of these futures awaits the universe is unknown, because we do not understand what dark energy is or why it has the value it currently has. The long-term fate of everything is genuinely uncertain. The neural correlates of empathy are still being mapped. Empathy, the ability to feel something of what another person is feeling, is fundamental to human social life. We have mirror neuron systems in the brain that activate both when we perform an action and when we observe another person performing the same action, and these systems have been proposed as part of the neural basis for empathy. But the complete picture of how empathy works in the brain, why it varies so much between individuals, how it differs from sympathy or compassion, and what neurological differences underlie conditions associated with reduced empathy are all questions that social neuroscience is still working through. Empathy is central to morality and to human relationships, and we are still in the early stages of understanding how the brain produces it. We do not know how the first stars formed after the Big Bang. The universe was a hot, dense soup of particles that expanded and cooled over hundreds of millions of years. The first atoms formed, and gravity began pulling matter together into clouds that eventually collapsed to form the first stars. These primordial stars, called population 3 stars, were made entirely of hydrogen and helium, the only elements that existed before any stars had yet lived and died. How exactly these first stars formed, what their masses were, how they influenced the surrounding gas and LED to the formation of the first Galaxies is something that astronomers are trying to reconstruct from theory and from the earliest observable light in the universe. The James Webb Space Telescope is revealing the early universe in new detail, but the full story of how the first stars were born is still coming into focus. The biology of sleep in marine mammals is not fully understood. Dolphins and other cetaceans need to breathe air, but they also need to sleep. How do they do both? Many cetaceans engage in what is called unihemispheric slow-wave sleep, where one hemisphere of the brain sleeps while the other remains awake, allowing the animal to continue swimming and surfacing to breathe. A dolphin can literally be half asleep and half awake at the same time. But how this extraordinary form of sleep actually works, how the brain maintains such a neat division, what the sleeping hemisphere is actually doing while the other is conscious, and whether dolphins also have something like REM sleep with associated dreaming are questions that cetacean biology is still working to answer. Sleep, already mysterious in humans, becomes even more so in animals who have evolved entirely different ways of achieving it. We cannot explain how certain savants acquire extraordinary skills. Acquired savant syndrome is one of the more startling phenomena in neuroscience. In rare cases following a brain injury, stroke, or infection, a person who showed no particular aptitude for art, music, or mathematics before the event suddenly develops extraordinary abilities in one of these areas. One person after a head injury began painting with extraordinary skill. Another began performing calendar calculations instantly. The emergence of these abilities following brain injury suggests that exceptional talents may in some sense be latent in many brains suppressed by normal neural function and revealed only when certain inhibitory circuits are disrupted. What this means about the nature of human potential and what the neurological mechanism is that either conceals or enables these abilities is still not understood. The mechanism of acupuncture is scientifically uncertain. Acupuncture, the practice of inserting needles at specific points on the body, has been used in Chinese medicine for thousands of years. Research into whether and how it works has produced genuinely complicated results. Some well-designed studies show benefits for certain conditions, particularly pain, that are greater than those seen in control groups. Others show that the specific placement of needles, the thing that is supposed to matter most according to traditional theory, may not be as important as practitioners claim. Whether the effects of acupuncture are due to specific physiological responses triggered by needle placement to a particularly powerful form of placebo effect, or to some combination of both is still debated in the scientific literature. The question of how and whether acupuncture works is genuinely unresolved. We do not know if the universe is deterministic. Quantum mechanics introduces fundamental randomness into nature. When a radioactive nucleus decays, when a quantum event occurs, the outcome is not predetermined by the prior state of the universe. It is genuinely random, or at least appears to be. This suggests the universe might not be deterministic, that the future is not in principle fully fixed by the present. But this is not universally agreed upon. The many worlds interpretation of quantum mechanics, for example, is deterministic. All outcomes occur, and what looks like randomness is just the branching of the universe into parallel realities. Hidden variable theories propose that quantum mechanics is an incomplete description and that underlying reality is deterministic. After all, whether the universe is fundamentally deterministic, whether the future is fixed or genuinely open, is one of the deepest questions in the foundations of physics and has no consensus answer. We cannot explain the specific details of how the moon affects biological rhythms. The moon's gravitational pull is responsible for the tides. This is well understood, but the claim that the moon influences human biology beyond this through its light and its gravitational effects in ways that affect sleep behavior and health is both ancient and contested. Some studies have found correlations between lunar cycles and sleep patterns, suggesting that people sleep slightly less and less deeply around the full moon, even in controlled environments without direct moonlight exposure. But other studies have found no such effect. whether there is a genuine biological rhythm in humans that tracks the lunar cycle, and if so, what the mechanism is genuinely unsettled. The moon may influence us in subtle ways that our methods have not yet been sensitive enough to clearly detect or rule out. We do not fully understand how eyes evolved. Eyes have evolved independently many times in the animal kingdom, invertebrates, insects, mollusks, and many other lineages. This convergent evolution, such a complex organ, has fascinated biologists and was once thought to pose a challenge to evolutionary theory. Darwin himself addressed this concern and argued that a gradual evolution from simple light-sensitive patches to complex, imaging eyes was entirely plausible, and subsequent research has strongly supported this view. But the details of how eyes evolved in specific lineages, what the intermediate stages looked like, and how the extraordinarily precise optical systems of eyes, like the vertebrate eye, came to be through gradual selection, are still areas of active research. The evolution of vision has left a detailed story in the diversity of eyes across the animal kingdom, and we are still reading it. We do not know why we have the particular number of senses we have. Humans are typically said to have 5 senses, but this is an oversimplification. We also have proprioception, the sense of where our body parts are in space. We have thermoception, the sense of temperature. We have nociception, the sense of pain. We have balance. We have the ability to sense our own heartbeat and other internal states through what is called interoception. Some researchers count more than 20 distinct senses when all of these are included. What we do not have is a magnetic sense which some birds and fish possess. We cannot detect ultraviolet or infrared light as many animals can. A specific combination of senses that humans have, and why evolution arrived at this particular set and not another, reflects our evolutionary history in ways that are still being traced. The boundaries of human perception and what lies just beyond them remain an interesting open territory. The most personal mystery is why experience feels like anything at all. We come at last to the mystery that contains all the others. You are here. You are aware. You are listening to these words, feeling the weight of your body, the warmth around you, the particular quality of this moment in the darkness, the texture of the fabric you are lying on the way. Sound reaches you from some slight distance, the particular quality of your own breathing, the rise and fall of it, the almost imperceptible rhythm. Something is happening that is not merely mechanical. There is a texture to experience, a quality of being present that no description from the outside captures. When a camera films a scene, nothing in the camera feels it. When a computer processes language, nothing in the computer understands it. But when you hear these words, something in you is there for them. Why? That is why the universe, through billions of years of physics and chemistry and biology, produced creatures who don't just process information, but feel, who don't just respond to stimuli, but experience them. Why the lights came on inside is the deepest question that has ever been asked. The hard problem of consciousness is not a gap that will be closed by a better measurement or a more powerful telescope. It asks something more fundamental, not how the brain works, but why there is someone home inside it, why there is something it is like to be you. Not what neurons do when they fire, but why firing neurons give rise to the felt quality of seeing red or hearing music or lying quietly in the dark with your thoughts trailing away towards sleep. Every other problem in science, however difficult, has the same basic form. Something happens and we want to understand the mechanism, but this problem asks something different. Even if we could describe every mechanism in perfect detail, the mystery would remain. Why does any of it feel like something from the inside? Science may eventually find ways to approach this question from directions we cannot yet imagine, or it may be that some aspects of this mystery are simply beyond what any finite mind can fully grasp about itself. You cannot fully step outside your own consciousness to examine it. The eye cannot see itself. And yet the fact that you are here in the dark, aware of your own awareness, is perhaps the most remarkable thing in the known universe. Not a star, not a black hole, not the structure of space-time, but this the simple, extraordinary, completely inexplicable fact that there is something it is like to be you right now, in this moment, slowly drifting towards sleep. So, dear listener, we reach the end of our journey through the unresolved 100 mysteries that no textbook can close with a confident final sentence. From the origin of life to the arrow of time, from the depths of the ocean to the depths of the self, from the silence of the cosmos to the noise of the dreaming mind, we have wandered together through the most beautiful unanswered questions that science has ever asked. It has been a long walk and a quiet one, and I hope that somewhere along the way, among the black holes and the migrating birds and the sleeping dolphins, among the equations and the ancient ice ages and the snowflakes falling through air, something landed softly in you. Not knowing can feel uncomfortable in the daylight hours and the bright, busy world of plans and schedules and things that need to be done. Mystery can feel like a problem to be solved rather than a place to rest. But here in the quiet and the warmth of wherever you are right now, it feels like something else. It feels like space, like breathing room, like the night sky itself, which is not diminished by how much of it remains unknown, but made more luminous by it. The stars do not need to be explained to be beautiful, and neither do you. You are right now a mystery to science, your consciousness, your dreams, your sense of being exactly yourself in exactly this moment. The fact that there is something it feels like to be you lying here in the dark is among the most profound, unsolved questions in the known universe. That is not something to find troubling. That is something to hold gently with a kind of quiet wonder, the way you would hold something small and luminous in the palm of your hand. Every scientist who has ever puzzled over the hard problem of consciousness, every philosopher who has stayed up late turning this question in their mind, every poet who has tried to put the interior of experience into words, all of them have bumped against the same soft, extraordinary wall. There is no complete answer, but the question itself is beautiful, and you simply by existing and being aware are at the center of it. The questions will still be there tomorrow. The wondering will still be there. Researchers are at work right now in labs and field stations and observatories and libraries, pushing a little further into each of these 100 territories someday, perhaps in your lifetime, or perhaps long after some of these doors will open. There will be a moment of astonishment, a collective breath drawn by an entire species that suddenly knows something it did not know before. That is the gift science gives eventually to those patient enough to wait. But even that knowing, when it comes, will almost certainly open new questions, because that is the nature of this place we live in. Every answer is also a door. But right now, all of that is tomorrow's business. Right now, all you need to do is let your breath slow, let your thoughts drift. Let the unsolved and the unknown become background music, soft and deep like rain on a rooftop over a very warm room. Let the questions become stars too many to count, too distant to touch, beautiful simply by being there. You have traveled a long way through the mystery tonight, through the strangeness of quantum mechanics and the silence of the cosmos, through the puzzle of the human brain and the extraordinary patience of a Greenland shark, through the unreasonable beauty of mathematics and the unreasonable beauty of a piece of music that makes you cry for reasons you cannot name. That is a lot of territory to cross, and you did it gently, without needing to solve anything, without needing to arrive anywhere. You are just here listening, breathing, letting the wonder move through you the way wind moves through a field of long grass, without disturbing a single root. That is enough. That has always been enough. Rest. Now let the questions float above you, like stars, beautiful and unhurried, asking nothing of you in return. Let whatever still unresolved corner of your own day drifts up toward the ceiling and dissolves quietly into the dark. The day is done. The world can carry its own mysteries. For a few hours, you are allowed to simply be here in the pause between questions, in the soft and welcoming place that has no name and needs none. Close your eyes, breathe, and let whatever comes next come gently, the way understanding always does in the quiet, when you are not trying, in the soft and unguarded country just before sleep. The universe with all its open questions and its still unlit rooms is in no hurry, and neither are you. If you are still awake, the next video will be waiting for you when you are ready. But if your eyes are already heavy, then let them close. Let the darkness be gentle. The mystery be your companion into rest. Good night.